Radioactivity Part 1. A. H. Becquerel discovered radioactivity in 1896 purely by accident. Henry Becquerel was using naturally fluorescent minerals to study the properties of X-rays, which had been discovered in 1895 by Wilhelm Röntgen. He exposed potassium uranyl sulfate to sunlight and then placed it on photographic plates wrapped in black paper. When Becquerel developed his photographic plates, he was surprised to find that the images were strong and clear, proving that the uranium emitted radiation without an external source of energy, such as the sun. Becquerel had discovered radioactivity. Later on, many more experiments were performed, and it was established that radioactivity was a nuclear phenomenon in which an unstable nucleus undergoes decay. This is referred to as radioactive decay. Three types of radioactive decay occur in nature. 1. Alpha decay, in which a helium nucleus 2He4 is emitted. 2. Beta decay, in which electrons or positrons are emitted. 3. Gamma decay, in which high energy photons are emitted. Law of radioactive decay. It is found that the number of nuclei disintegrating per unit time is proportional to the number of nuclei in the sample. In a sample of a particular radioisotope, the number of decay events minus dn expected to occur in a small interval of time dt is proportional to the number of atoms present n. Minus dn by dt is proportional to n, or dn upon dt is equal to minus lambda n. Equation 1. The negative sign indicates that n decreases as time increases, as the decay events follow one after another. Lambda is called the radioactive decay constant or disintegration constant. Now, integrating both sides of the equation 1, we get integral dn by n is equal to minus lambda integral dt. Log n t is equal to minus lambda t plus c. Equation 2. Or log n t minus log n naught is equal to minus lambda t minus t naught. Equation 3. Here n naught is the value of n at time t naught, and n t is the number of radioactive nuclei at any subsequent time t. Setting t naught is equal to 0 and rearranging equation 3 gives us log n t upon n naught is equal to minus lambda t, which gives n t is equal to n naught e raised to power minus lambda t. Equation 4. Decay rate. Decay rate R is defined as R is equal to minus dn t upon dt. For a given element, the decay or disintegration rate is proportional to the number of atoms. Decay rate gives us the number of nuclei decaying per unit time. Differentiating equation 4, we find R is equal to lambda n naught E raised to power minus lambda T, equation 5, or R is equal to R naught E raised to power minus lambda T. Here, R naught is the radioactive decay rate at time t is equal to 0, and R is the rate at any subsequent time t. We can now write equation 5 as R is equal to lambda n. The total decay rate R of a sample of one or more radionuclides is called the activity of that sample. The SI unit for activity is becquerel, named after the discoverer of radioactivity, Henry Becquerel. It is defined as 1 becquerel is equal to 1 BQ is equal to 1 decay per second. An older unit, the curie, is still in common use. 1 curie is equal to 1 Ci is equal to 3.7 into 10 raised to power 10 BQ decays per second. 1 curie represents exactly 3.70 into 10 raised to power 10 disintegrations per second. Half-life. Half-life is the time at which both N and R have been reduced to 1/2 their initial values. Nt is equal to N naught E raised to power minus lambda T. When T is equal to T12, N is equal to N naught upon 2. N naught upon 2 is equal to N naught E raised to power lambda T half. 1 upon 2 is equal to E raised to power lambda T half. Lambda T half is equal to log 2 base E. T half is equal to log 2 upon lambda is equal to 0.693 upon lambda. Mean life. Mean life is the time at which both N and R have been reduced to E raised to power minus 1 of their initial values. Mean life tau is equal to 1 by lambda. T half is equal to log 2 upon lambda is equal to tau log 2.